So let's do a nice example. And so I want to take a look in chapter 15. We're going to take a look at number 42 and 15. Okay. And so it reads that we have a gas in a cylinder is held at a constant pressure of 2.30 10 to the 5th pascals. So we have gas in a cylinder. And then they tell us that our pressure is 2.30 times 10 to the 5th pascals. And then more importantly, they tell us that this is a nice constant pressure, which is really nice because we have a formula for the amount of work done by the gas if the pressure is constant. So this tells me I have my formula. Okay. Let's see if we're going to need it. Let's keep reading though. It says that the gas is cooled and compressed from 1.70 10 to the third, 1.70 cubic meters to 1.20 cubic meters. So we're going to cool the gas and then compress the gas. Okay. Now, since we're going to compress the gas, what does that tell us about the work done by the gas? Remember, the gas is going to push out on that piston, and if we're going to compress it, then what kind of work did the gas do on the environment? Yep. It's going to do nice negative work. It's going to push out as it goes in. So nice negative work, 1.20 cubic meters. Okay. And so then it asks, the internal energy of the gas decreases by 1.40 10 to the 5th joules. And so since this is decreases by, what does that tell me about my change in the internal energy? Yep. And there we go. And so then the questions that it asks us to find are, what's the work done by the gas? Again, this is by the gas. So that's an important piece to know. And then find the amount of heat that either flowed into or out of the gas and state which way the heat flowed. All right, so we want to calculate the work done by the gas. Okay. And whether it went into the gas or out of the gas kind of things. Okay. So for this particular one, then we can go in and we talked about the fact that, there's my cylinder picture. There's the picture. And on the next page, this is where we got that the work done by the gas was the pressure times the change in volume. And this is automatically gives us the correct sign, because if the final volume is greater than the initial, you do final minus initial. This is positive times your positive pressure, gives you a positive work because it expanded. And if the final volume is less than the initial volume, then the delta volume will be negative and you get negative work done by the gas. So it auto gives you the correct sign. And so then let's go in and calculate that. So this is the work done by the gas. This would be on the environment if they ask for that. And so this is our pressure times that change in volume. And this is only if the pressure is constant, which it is. And so this is our 2.30 times 10 to the 5th pascals. And then our volume change, it's going to go from this to that. So it's final minus initial. Notice it's in SI units. So that was very polite of them. Half the times they're going to be in wrong units, and we'll need to convert them into cubic meters to be able to do the correct things. And I would expect that there's going to be lots of liters. So it's got to be kind of careful. And the way that it goes is that 1 milliliter equals 1 centimeter cubed. And it's a factor of 1,000,000 cubic centimeters to a cubic meter, but it's only a factor of 1,000 milliliters to a liter. And so then what you end up with is you end up with like 1,000 liters is 1 cubic meter. I mean, picture, waist high, length, width, depth, and a liter's a liter bottle. And so there's going to be 1,000 of them in there. So that's just the way it goes. It's not too difficult, but we have to be careful. This is all SI. And so it'll automatically give us the correct sign. It is going to be negative because we're compressing. And how much? Oh, this isn't too bad. That's what? That's half. So half of this is 1.15. Did I do that right? Excellent, excellent. So there's our answer for A. And then we need the heat. And so then what we're going to do is we're going to go in and take a look at our first law of thermodynamics. So we have the change in U is Q minus W. And so then I could just move this work over to here. And this will allow us to solve for Q. And so then what that gives me is that our amount of heat is going to be equal to this change in the internal energy plus the amount of work done, again, by the gas on the environment. And so then our heat amount, this was, since it decreased by this amount, was a negative 1.40 times 10 to the 5th. So that's our delta U. Then we're going to add on the work, which is also a negative 1.15 times 10 to the 5th. And so then this will give us a definite negative. And what do we get? These are 10 to the 5th. So this is going to be 2.55. 10 to the 5th joules. Okay. And so what does this tell us? So what you have to remember is what was the Q. Okay, so that's how we can easily decipher this result. And this is the thing, is that a lot of this is in these English phrases. And the English phrases predominantly determine things like signs. And so that's the hardest bit of these problems, are the signs. Since this was the heat added to the system, and so then if it's negative, then what does that tell us? Yeah. Yeah, if it's negative added, then that means it was removed. Or we could say that it's what? So instead of saying it was removed from the gas, we could say that it was what? Yeah, it was added to the environment, because you're either in the system or you're in the environment. There is no other place to be. So it was removed from the gas. Or you could say it was added to the environment, kind of things. Are we good?